graphs of many functions are nonlinear. However, we can use linear approximations of these nonlinear functions to analyze what's going on over small intervals of x values, which brings us to the average rate of change. Now, to begin, let's suppose that we have two ordered pairs, x sub 1, y sub 1, and x sub 2, y sub 2, on the graph of such a nonlinear function. And we'll define this nonlinear function as y equals f of x. So with this, we can convert our ordered pairs to function notation form by replacing each y with f of x. So our first point becomes x sub 1, f of x sub 1, and our second point becomes x sub 2, f of x sub 2. And we'll label these points on our graph. Now, if a function is defined on an interval from x sub 1 to x sub 2, we have the following. So we say that the average rate of change of our nonlinear function f on an interval from x sub 1 to x sub 2 is defined as the slope of the secant line passing through these two ordered pairs. Now, what is the secant line? Well, again, we're passing through our two fixed points. So connecting those ordered pairs with a straight line, we can see our secant line. Now, we know how to find the slope of a line, so we can find the average rate of change of our function simply by finding the slope of the line passing through these 2 points. And we can conclude that the average rate of change is the slope, which again we know is the change in the y values by the change in the x, or y sub 2 minus y sub 1, all over x sub 2 minus x sub 1. And now replacing these y's with our function notation, we have f of x sub 2 minus f of x sub 1, all divided by x sub 2 minus x sub 1. And of course, we want to keep in mind that division by 0 does not exist. So we'll add here that, of course, x sub 1 cannot be equal to x sub 2. We can see here that the average rate of change of a function is simply an adaptation of the slope of a line.